Ma'am, make me a host, yes.
Good evening, sir. You can start now, sir.
Dhanalakshmi, what happened to your result? Text me. All right. Today, I thought we'll continue with the questions yesterday, what we started with, but it's only very few questions. So I thought I will discuss a synopsis on the first PUC topics, thermodynamics, and we'll work some of the questions based on thermodynamics. Thermodynamics, chemical equilibrium, and redox reactions. We need to discuss some of the questions. So we shall work on it, the synopsis part of thermodynamics. The thermo stands for heat. Dynamics stands for motion. Thermodynamics refers to the study of energy change or heat change in a process is called as thermodynamics. Now, for an example, now if we take a conical flask like this, and in this conical flask we have HCl, and in the burette we have NaOH. When NaOH is added into the burette and to the conical flask, that NaOH will react with HCl to form NaCl and water. And this is a neutralization reaction. Always neutralization reaction is exothermic. Now, what happens is exothermic heat is liberated during this process. So heat goes out of the conical flask. Now, the HCl which is in the conical flask will be called as system. Outside the conical flask, everything will be called as surrounding. That means heat travels from system to surrounding. So system is specified portion of matter which is under study is called a system. So from the system, if energy is given to the surrounding, this is first case. Now, if we take a container in which we have a gas, and this is fixed with a piston, you apply more pressure. So work is done on the system. What happens now? The piston will move down and the gas gets compressed. So here, the work is done on the system. So if there is a transfer of energy from the system to surrounding or from surrounding to the system, and then we call that process as thermodynamics. So thermodynamics refers to a part of the universe which is under observation, and the remaining of the universe constitute of surrounding. I told you system is defined as specified portion of matter. Specified portion of matter which is under study. Now we take 10 ml of HCl in the conical flask. This 10 ml of HCl which is in the conical flask will be called as a system. Other than the HCl which is in the conical flask, everything outside the conical flask will be called as surroundings. So rest of the universe other than the system is called as surroundings. So system and surrounding together is called as universe. So thermodynamics includes the study of different form of energy and energy transformation. Most commonly heat into work and work into heat is called as thermodynamics. See here in this case, it is heat transferred to the system. In this case, work done on the system. Heat into work and work into heat will be called as thermodynamics. Now, there are three types of systems. Three types of system. One is a closed system, the other one open system, and the other one is isolated system. First, we will talk about open system, a system in which both matter and energy can be exchanged with surrounding. Those kind of systems are called as open system. Now, cup containing water, a cup containing water, into the cup, you can add water or you can remove water. You can heat the cup or you can cool the cup. So both matter can be exchanged as well as energy can be exchanged. Those kind of systems are called as open system. Both energy and matter can be exchanged with the surroundings. Those are called as open system. When we talk about closed system, only energy can be exchanged. Energy can be exchanged, but not matter. So those are called as a closed system. Just an imagination, a cup of water in which the cup is closed with the lid. If the cup is closed with the lid, we cannot add water into the cup nor remove the water from the cup. But we can heat the cup or we can cool the cup. Those kind of systems are called as closed system. Only energy can be exchanged, but not matter. Isolated system, no energy nor matter can be exchanged. So those are called as isolated system. Thermos flask is an example for isolated system. Now, what is the state of a system? A state of a system is a measurable properties of the thermodynamic system that must be specified to make an useful calculation. So we have, firstly, before we talk about the other concepts, we need to understand a process. A process can be defined as change in state or change in phase can be called as a process. This is important. Now we have different types of process. One is isothermal process. Iso means same, thermal means heat. So a process which takes place at constant temperature. A process which takes place at constant temperature is called as an isothermal process. In an isothermal process, delta T is 0. Change in temperature is 0. Now, the next is adiabatic process. All this you should remember. Adiabatic process. In adiabatic process, a process which takes place at constant heat. Constant heat. Heat is represented by Q. Delta Q is equal to 0 for an adiabatic process. So a process which takes place at constant heat is called as adiabatic process. Next, we have isochoric process. So isochoric process, iso same chor volume. A process which takes place at constant volume is called as isochoric process. Next, we have isobaric process. In this isobaric process, pressure is maintained constant, or change in pressure is 0. Delta P is equal to 0. A process in which the pressure is maintained constant is called as isobaric process. A cyclic process. A cyclic process undergoes many number of steps and finally comes back to its original state after a number of steps. Such processes are called as such processes are called a cyclic process. Cyclic process, a process will take place in many steps, and finally the system returns to its original state. Those are called as cyclic process. In case of cyclic process, change in internal energy is 0 and change in enthalpy is also 0. Remember, in a cyclic process, change in internal energy is 0 and delta U or sometimes we can represent it as delta E also. So internal energy, we will learn what is internal energy in few minutes time. So in case of cyclic process, change in internal energy is zero, as well as change in enthalpy is zero. Next, a reversible process and an irreversible process. A reversible process is a process in which the direction of the reaction can be reversed at any stage is called as reversible process. Irreversible process, a process which cannot be reversed, which takes place only in one direction, is called as irreversible process. Now remember, for a cyclic process, delta U is zero and delta H is also zero. Different types of processes we have learned. Now the coming to internal energy. Now, what is this internal energy? This internal energy is represented as U, or it's also represented as the letter E. What is this internal energy? Now, each and every reactant will contain different types of energies. So internal energy is simply defined as total energy in the system. Total energy in the system is called as internal energy. So this internal energy is the sum of kinetic energy, potential energy, vibrational energy, translational energy, electronic energy, all this. So sum of all the energies will be called as internal energy. So simply it is defined as energy stored in a system. So it is difficult to find the internal energy. So change in internal energy is determined. Change in internal energy is given by the formula internal energy of the product minus internal energy of the reactant. So change in internal energy is determined by internal energy of the product minus internal energy of the reactant. Now you should remember the first law of thermodynamics. First law of thermodynamics. So the first law of thermodynamics states that energy can be neither created nor destroyed. It is also called as law of conservation of energy. So energy can be neither created nor destroyed. The mathematical representation of in the first law of thermodynamics is delta U is equal to Q plus W, or delta U is equal to Q minus W. Delta U is equal to Q plus W, or delta U is equal to Q minus W. Now, the sign convention. You should remember the sign convention. If it's an endothermic process, heat is absorbed. When we say heat is absorbed, delta H is positive. Exothermic reaction, heat is liberated. When heat is liberated, delta H is negative. Now, this is important. Work done on the system. Work done on the system. When work is done on the system, W is positive. And when work is done by the system, when I say work is done on the system, compression. If gas is compressed, it's called work is done. So when work is done by the system, it means expansion. It happens itself. So gas expands. So when work is done by the system, work done has a negative value. Work done has a negative value. So this is the sign convention. Now, in case of isothermal process, how do we calculate the work done? What's the formula to calculate the work done? In isothermal, reversible expansion. Reversible expansion. In isothermal reversible expansion of an ideal gas, work done is calculated by the formula minus of P into TV. Minus of P into TV. Pressure, external pressure into change into volume. Change of volume. Minus P into T. So if we integrate this, we get work done as W is equal to, we get the work done as minus 2.303 nRT log to the base 10 of P1, P2, P1 by P2. Or this also can be written in terms of volume minus 2.303 nRT log to the base 10 of V2 by V1 in terms of volume and in terms of pressure. This minus sign indicates work is done by the system. If work is done on the system, W becomes positive. So this is with respect to the first law of thermodynamics, in which we need to know the formulas to work out some problems. Now coming to enthalpy. Enthalpy, how enthalpy is related? Enthalpy is nothing but the heat content of the system. Now, enthalpy is a heat content of the system. The enthalpy is related to pressure by the formula. Enthalpy is equal to U plus P. U is internal energy, P is pressure, and V is volume. But it's difficult to find the enthalpy. So change in enthalpy is given by the formula delta H is equal to delta U plus P into delta V. So in gaseous terms, otherwise we can write delta H is equal to delta U plus of, we know that PV is equal to RT. PV is equal to nRT. Therefore, we can write as delta N gaseous moles RT. So these are the formulas which you should remember to work out the relation between enthalpy, pressure, volume. Now, in order to understand a few more concepts, we should know properties called as intensive property and extensive property. Now, what is this intensive property and extensive property? Intensive property, property which does not depend on mass. The depend on amount is called as intensive property. A property of a system which does not depend on the amount. Now, for an example, temperature does not depend on the amount of water, or density does not depend on the amount. Surface tension does not depend on the amount. Refractive index does not depend on the amount. Right? These all are examples for intensive property. Now, extensive property, when we say it is the property of a system which depends on the amount, or quantity. Those are called as extensive property. Now, example for extensive property, heat is an example for extensive property. Heat, otherwise it's called enthalpy. Enthalpy is an example for extensive property. Entropy is an example for extensive property. Volume is an example for extensive property. Mass is an example for extensive property. So, internal energy is also an example for extensive property. Heat capacity is also an example for extensive property. So intensive property means property of a system which does not depend on the amount is called as intensive property, and extensive property, when we say a property of a system which depends upon the amount, is called as extensive property. Now you should remember this one, measurement of delta H and delta U. It's by calorimetry. Calorimetry. CALORIMETRY, calorimetry. Calories, instrument which is used to measure the calories. Now, delta U, or change in internal energy, is calculated or experimentally founded by a bomb calorimeter, B-O-M-B, bomb calorimeter. The final expression is delta U is equal to C into delta T into m by m. Now, m is the mass of the substance taken, m is the molecular mass, c is the heat capacity, delta T is the change in temperature. So C is heat capacity, delta T is change in temperature, M is the molar mass or molecular mass, and small m is the mass of the substance, taken. So this is the formula to calculate the change in internal energy by calorimeter. Now we'll work some of the problems in a few minutes time. Now you need to know different types of combustion, different types of enthalpies. The first one is enthalpy of combustion. Enthalpy of combustion. What is enthalpy of combustion? The amount of heat liberated when 1 mole of a compound is combusted is called as enthalpy of combustion. Second one is, in case of enthalpy of combustion, one more we like enthalpy of neutralization. Enthalpy of neutralization. See, enthalpy of combustion and neutralization, these two enthalpies are always exothermic. These two enthalpies are always exothermic. Always heat is liberated. Other enthalpies, what we are learning, heat can be liberated or it can be absorbed. Now, enthalpy of atomization. Enthalpy of atomization. Now, what is this enthalpy of atomization? It is a change in enthalpy on breaking 1 mole of bonds. On breaking 1 mole of bonds completely to obtain atoms in gaseous phase. So now, for an example, if you take methane, this methane, the energy required to break carbon, methane has structured 4 bonds like this. So 1 mole of methane, in order to break all the bonds so that we get the elements in their atomic state and in gaseous state, is called as enthalpy of atomization. So bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bond of gaseous covalent compound is broken to form products in gaseous state. So bond enthalpy of atomization and bond dissociation enthalpy is different. So in case of atomization, enthalpy of breaking 1 mole of bond completely. 1 mole of bond completely. Bond dissociation enthalpy, it is the energy or enthalpy required when to break 1 mole of covalent bonds. The bond dissociation enthalpy is specific with respect to covalent bond. Now the fourth is enthalpy of solution. Enthalpy of solution. So the amount of heat change observed when 1 mole of a solute is added into 1 mole of 1 liter of the solid. So enthalpy of solution is given by the formula enthalpy of lattice enthalpy plus enthalpy of hydration. So enthalpy of solution is lattice enthalpy plus enthalpy of hydration. Lattice enthalpy, you would have learned it in chemical bonding chapter. It's called as Born-Haber's cycle. How do you form lattice energy? How do you find lattice energy? Now, here in this chapter, we need to understand few more concepts. That is spontaneity of the reaction. Spontaneity of the reaction or spontaneity of the process. Now, the spontaneity of the process is based on free energy. G is the representation of free energy. So delta G, if it is negative, then the reaction is spontaneous. If delta G is positive, it is non-spontaneous. And if delta G is 0, the system is in equilibrium. Now, delta G is found out by the formula Gibbs equation, delta H minus T into delta S. Delta H is enthalpy change, T is temperature. What is this delta S? This delta S is change in entropy. Entropy is nothing but the measure of disorders. Measure of disorders. Entropy is given by the formula heat of a reversible reaction by temperature. Change in entropy is given by the heat of a reversible reaction with respect to temperature. We have various formulas to calculate the change in entropy. The change in entropy of fusion is given by enthalpy of fusion by melting point. Temperature at which it starts melting. So likewise, enthalpy of vaporization is given by entropy of vaporization is given by enthalpy of vaporization by boiling point. TB is boiling point. Likewise, entropy change during sublimation is given by enthalpy of sublimation by the temperature. So these are the formulas to calculate the entropy change. The entropy change. Based on this Gibbs equation, delta H is equal to delta G is equal to delta H minus T into delta S. Now, two more formulas you should remember. Now, based on these two more formulas, remember, and then we'll work few of the problems. Now, coming to the other formula, the free energy and electron potential. Delta G naught is equal to minus NF E naught. E is the electrode potential or standard EMF of the cell. Standard EMF of the cell. And we have to have one more relation, that is delta G naught is equal to minus 2.303 RT log of K. K is the equilibrium constant. So these formulas, if we can remember, we can work out the problems based on thermodynamics. Questions based on thermodynamics. The theoretical part of questions you can learn. One or two questions, few questions I will teach you. I will write the question on next week. Now coming to the first question. The work done during the expansion. See, it's expansion. That means work done will be negative. Work will be done by the system. Expansion of gas from 4 decimeter cube to 6 decimeter cube against a constant external pressure. Constant external pressure of 3 atmospheres. Constant external pressure of 3 atmospheres is 3 atmospheres is 3 atmosphere is. In brackets, they give 1 liter atmosphere is equal to 101.32 joules. Now, they've given various options. They've given options as minus 6 joules. B, they've given us minus 608 joules. C, they've given plus 304 joules. And D, they've given minus 304 joules. 304 joules. Now, this is expansion. Truly, it is expansion. So the value will be in minus sign. So this is ruled out. So work done is calculated by the formula minus of P external into delta. That is minus of P external into final volume minus initial volume. So the pressure external, they have given as 3 atmosphere. So it is minus 3. Final volume is 6 and initial volume is 4. It is 6 minus 4. So it will be 6 atmosphere, liter atmosphere, 6 liter atmosphere. Volume is in liter and pressure is in atmosphere, 6 liter atmosphere. Here they've given 1 liter atmosphere is 101.32 joules. So work done in terms of energies, 6 minus 6 into 101.32. So that will be equal to minus 608. You will get 608 joules. Therefore, the answer for this question is option B. It is minus 608. The next question. The next question. Now, 2 liters of an ideal gas. 2 liters of ideal gas at a pressure of 10 atmosphere expands isothermally into vacuum. Until its total volume is 10 liters. Total volume is 10 liters. How much of heat is absorbed and how much work is done in the expansion? The options for this is, we've given the options to be A, 10 joules, 10 joules, B, 8 joules, 10 joules, C, 0 joules, 0 joules, and D, it is 18 joules and 0 joules. Now, in case C, the question clearly says into vacuum. When it is in vacuum, pressure external is 0. When pressure external is 0, work done is 0 minus P external into final volume minus initial volume. This is the formula. Since we are talking about in vacuum, pressure external is 0. When pressure external is 0, work done is 0. So when work is heat absorbed is also 0. Q is also 0. And work done is also 0. Therefore, the answer is option C. The next question. Consider the following equipment. Consider the following reaction. Consider the following reaction. The reaction is carbon monoxide gas. When it's combusted with oxygen, gives you carbon dioxide gas. How delta H and delta U are related? How delta U and delta H are related for the reaction. So they've given the options. Delta H is equal to delta U minus 0.5 RT. B, delta H is equal to delta U minus RT. C, delta H is equal to delta U plus 0.5 RT. D, delta H is equal to delta U minus 1.5 RT. So now this is a reaction. Now in this reaction, all the reactants and products are in gaseous state. So delta N will be number of moles of gaseous product minus number of moles of gaseous reactant. So number of moles of gaseous product, we have carbon dioxide 1 mole, minus number of moles of gaseous reactant, it is 1 plus 0.5. So it will be minus 0.5. Delta N will be minus 0.5. So how it is related now? So delta H will be equal to delta U. Delta N is the formula. So the relation is plus delta NG RT. This is the formula. Since delta NG is minus 5, it can be written as delta U minus 0.5 into RT. So therefore, the answer is option A, the first option. So remember, delta N is only with respect to gaseous molecule. It is not with respect to liquid or solids. It's only with respect to gaseous molecules. The next question. Will you erase this? Next question. For combustion of 1 mole of benzene at 25 degrees Celsius, the heat of reaction at constant pressure, is minus 780.9 kilocalories. Minus 780.9 kilocalories. What will be the heat? What will be the heat of reaction at constant volume? What will be the heat of reaction at constant volume? For combustion of 1 mole of benzene at 25 degrees Celsius, the heat of reaction at constant pressure is 780.9 kilocalories. So heat at constant pressure is equal to heat at constant volume plus delta NGRT. Or we can write heat at constant volume is equal to heat at constant pressure minus delta NGRT. So heat at constant pressure, they've given minus 780.9 calories. Minus of delta Ng for this reaction. Benzene is C6H6. Benzene is a liquid. When it is burned with oxygen, you get carbon dioxide and water. Carbon dioxide and water. So it is 7.5 moles of oxygen here. Carbon dioxide is 6 moles and water is 3 moles. Water is a liquid here. Carbon dioxide is a gas and oxygen is also a gas. So delta N is minus 5. That is 6 minus 7.5. It is minus 1.5. So it's minus of minus 1.5. R value is 2 into 10 power minus 3 in terms of calories and 25 degrees Celsius. Temperature is 25 degrees Celsius, 298. So when we simplify, we get the R value minus 780.0 kilocalories. See, they've given the R values in the options, they've given the R values in calories. That is why I have taken R value as 2 into 10 power minus 3. If they've given the values, answers in terms of joules, then we will take R value as 8.314. Here they've given in calories. So this is the answer, 780 kilocalories. Next question. What will be the standard internal energy change? What will be the standard internal energy change? What will be the standard internal energy change for the reaction at 298 Kelvin? OF2 is a gas plus H2O gas, giving you O2 gas plus 2HF gas. Delta H naught is equal to minus 310 kilojoules. Options are A is minus 312.4 kilojoules, B minus 125.03 kilojoules, C minus 310 kilojoules, and D minus 156 kilojoules. So delta H naught is equal to delta U naught plus delta NG RT. So delta U naught, they're asking change in internal energy standard. Delta U naught will be equal to delta H naught minus delta NG RT. Delta H naught they've given us minus of 310 kilojoules. And for this reaction, 3 and 2, so delta N is 1. R value is 8.314 and temperature is 298. On simplification, the value we will get is 300 and minus 312.47 kilojoules. Hence, the answer will be option A. So we will learn the next concepts in the next class. Thank you. Ma'am, stop the class.